guys. Okay, so we're going to be learning a little bit more probability, just a few tricks of the trade. You have learned most probability. We've got about 2 more probability lessons. This one is really going to be about the binomial model for probability. So to start, what we're gonna do is just rehash what we did last time. So I'm gonna give you some information and we'll use that to calculate some probabilities. So let's talk about blood type. In the US, there are 44% of people that have type O blood. There are 42% of people that have type A blood. There are 10% of people that have type B blood, and there are 4% of people that have type AB blood. And if I add all of these up, I get 100%, so that is a full, complete model. So last video that we watched, we were able to answer questions like this. What is the probability that the first person at a blood drive out of 5 is the only type O? So we can picture our 5 people, 1, 2, 3, 4, 5. The first one is type O, 0.44, but that's the only type O person, meaning all the rest are not type O. Not type O. And we remember that not type O is everything except type O. So not type O would be 1 minus 0.44, which is 0.56. So basically what we're looking at is 0.44, and these are all multiplying. So times 0.56 to the 1, 2, 3, 4th power. And we can type that in our calculator. .0433. Okay, so this is how we did probability before, and we could also answer something like this. What is the probability that exactly 1 of 5 people is type O? The difference from this first one and the second one is that the first one tells you which person is type O. In the second one, I'll number these, in number 2, it doesn't tell you which person is type O. It's just that 1 out of 5 are type O. So if I'm going to list my 5, this one could be the type O person. Or the second one could be the type O person. Or, oh my gosh, this is going to go on forever. So what I need to think about is how many different ways can I make exactly one type O person? Because in every single circumstance, I'm going to have one type O and the rest are not type O. So in every single circumstance, I'm going to have the same multiplication rule, 0.44 times 0.56 to the 4th. Now I just need to figure out how many ways can I make that happen. Because really I'm saying I want one type O, so 1.44, and I want the rest of the 5, so the other 4, to be not type O. And that's over and over again. How many different ways can I make that happen? 1, 2, 3, 4, 5. 1, 2, 3, 5. So there are 5 different ways I can make it happen. It could be the first guy, the second guy, the third guy, the 4th guy, or the 5th guy. So what I'm saying is I have 5 different ways to make this outcome, meaning I have 0.44 times 0.56 to the 4th 5 times. 1, 2, 3, 4, 5. Okay, so how many ways it can happen, and then the probability that we're looking for. Technically, this is a binomial model, so we're going to see some more of this and find a faster way to do it. So what I'm doing is I'm saying I want 1 type O and 4 not type O, but I want that 5 times. And so the probability of getting exactly 1 type O person out of 5 is about 22%. Okay, so it doesn't have to be the first person. It could be any of those 5 people, but exactly one of them has to be type O. Okay, let's change it up just a little bit. And let's see, okay, what's the probability that out of 5, exactly 2 are type O? So if I change it, and now I'm saying exactly 2 are type O, it could be the first 2. 1, 2, 3, 4, 5. So it could be these 2. Or it could be the last 2. Oh my gosh, how am I going to figure out how many different ways I can make exactly 2 type O's? It could be the first one and the last one. Man, this seems really annoying. There's probably a better way. Well, there is. There is a function in your calculator that can tell you how many different ways you can make it happen. So what we're seeing is we want, every time we're going to get the same multiplication rule here. Every time we're going to say, okay, I want 2 that are type O, and I want 3 that are not type O. So it's 0.44 squared times 0.56 to the 3rd. Every time it's going to be like that. Now we just need to figure out, well, how many different times or how many different ways can we make this happen? So the way that we do that is something in our calculator. To show us how many different ways we can make this happen. How many ways can we make out of 5 2 successes? So what we do is we say, okay, calculator, I have a total of 5 in my sample, and I want you to make how many combinations of 2 successes? How many combinations of 2 successes can you make out of 5? So this is 5 in our sample. And this is number of successes. The success in this case would have been type O, because I want 2 type O's. So total sample and the number of successes. And so this is called a combination. What it does is it counts how many different ways you can make that combination of 2 type O's and 3 not type O's. So it's in your calculator under math. The first thing you probably need to do, though, is type your 5, your total in your sample, and then go to math and scroll over to probability, and it's number 3. And then you type in your number of successes. And it tells you how many different ways you can make that happen. So I could have written out, okay, well, could have written this out 10 different times, or I could just figure out how many different ways I can make it happen without actually finding the ways. So what I'm going to do is I'm going to say 10 times 0.44 squared times 0.56 to the 3rd. And that will be my solution. So 10 times 0.44 squared times 0.56 to the 3rd. 0.339, so 0.340. Okay, so what we're seeing is this kind of pattern shape up, where we're saying, okay, out of 5, so I know that in total I have 5, And what's cool is that these exponents will add up to 5, where I want this many successes and then this many not successes or fails. And so it creates this formula for us. And that's the binomial formula. So we're saying, okay, I have n total in my sample, and I want to figure out how many different ways I can make x successes. And so if p is our probability of success, our goal probability, I'm going to take p to the xth power because I want x successes. Okay, and so then I'm like, okay, then I want this many fails. So if p is success, we know that 1 minus p we can label as q. That's our fail. And we want the rest of them to be fails. So if we want x successes and there are n total, we want n minus x fails. Okay, and you don't need to memorize this formula, but it is there for us because what we will see is, okay, let's say I wanted to figure out what is the probability that out of, I don't know, let's go with 8 donors, 3 are type O. And we know that the probability of being type O is 44%. So if our success is type O, that's 0.44, what we're saying is we want 3 of type O's. So we want 0.44 to the third. We want 3 successes out of 8, meaning that the rest of them, so if there are 3 successes and there are 8 total, the rest of them are fails. So if 0.44 is success, 0.56 is fail, and the rest of them, which is 5 left over, those 5, 8 minus 3 is 5, those 5 are fails. And so this is the probability of getting 3 out of 8 to be type O. But there are so many ways to make this happen. So we need to actually add on, okay, out of 8, how many different combinations of 3 successes can I have? How many different ways can I make that happen? And I multiply these across to give me my answer. And this is a binomial probability. So I go, okay, 8, math, scroll to probability, choose 3 times, so there's 56 different ways to make that happen, times 0.44 to the third, times 0.56, oops, sorry, not used to this kind of calculator, times 0.56 to the fifth. So 0.263. So there's a 26% chance that out of 8 donors, 3 of them are type O. It doesn't matter which 3, just 3 of them are type O. Now you might be asking, okay, cool. So this is a quicker way to do that. Now you might be asking, okay, what if the question is, what is the probability that out of 8 donors, 3 or less are type O? Okay, another way to say that might be no more than 3 are type O. So if we're looking at 3 or less are type O, what we're looking at is, okay, what's the probability of 3 being type O? That's what we found up here. Or, meaning add, the probability of 2 being type O, or less, so I could keep going, or none being type O. So I want to add all of these up out of 8. So I'm looking for these, and I don't want those. So am I going to have to do this formula 4 different times. This seems like a hassle. I mean, I can. It just seems like a hassle. I would have to do 8 choose 3 times 0.44 to the third times 0.56 to the fifth. That's the probability of getting 3. Plus the probability of 2. So that means out of 8, I want 2 successes. So I want 2 type O's. And the rest, meaning 6, not type O's. And then do it again. This seems super annoying, Miss Shine. Isn't there a better way? You know there is, guys. So I got you. Hang on. I'll just write it all out for the heck of it. Okay, I could do all of this and type it all in my calculator, but there is a better way. And so what we're doing here by adding everything up is we're accumulating it. So kind of like your cumulative GPA, which adds up your GPAs from freshman year up to senior year, that we're gonna do the cumulative binomial probability. So this is really a distribution. So we're gonna go back to distributions where we have the normal distribution, second bars, and it's actually down here. See it? Binomial. Binomial cumulative CDF. So binomial CDF. So what we want to tell our calculator is, hey, Mr. Calculator, I have 8 total trials, or 8 total in my sample. The probability of success is 0.44. And I want you to accumulate up until my x gets to from 0 up to 3. So I wanted to stop adding at 3. 3. And it will calculate that probability for me. 0.5. Ooh, interesting. Okay, and so this is how we can do that cumulative probability. If we started adding all of these up, we would have gotten 0.5 or 50% chance. Okay. And so this is, it tells us everything to the left. It tells us everything on that left side. It adds up from 0 up to 3. So it does that for us, the cumulative probability. Now you might be asking, okay, Ms. Shine, well, what if I don't want 3 or less? Type O is actually the most desired blood type. Everyone can take on type O, technically type O negative, but a type O is the most desired, so I don't want 3 or less. I actually want 3 or more type O. So that would kind of be like saying at least 3 type O. So I want, out of those 8, I want 3 or more. So I want all of these. But my calculator can only start adding at 0. So how am I going to get the right side? Well, I can think of it as saying everything. I want everything, but I want to take away this left side. So I'm going to tell the calculator, okay, I want everything, 100% of all of my options. But I don't want 0, 1, and 2. So I don't want this cumulative probability, CDF, out of 8, with the probability of type O being 0.44, I want you to take away up to number 2. Okay, whereas this one, I wanted the left side, so it was just given to me. I want out of 8, I want up to number 3. That gave me this. However, if I want to find the right-hand side, the more than side, I need to do 1 minus what I don't want. Okay, so the at least problems, or more than problems, we should always think about 1 minus still. Okay, we thought about that before, and now we're doing it again. Okay, so I would just type that in my calculator. 1 minus, go to second vars, binomial CDF. What I don't want is out of 8, my probability of success is still 0.44. I want to take everything away up to number 2. So it's like adding probability of 0 plus probability of 1 plus probability of 2 and taking that away, 0.76. So there's actually a 76% chance that I get 3 or more type O. So there's a good chance that I get a lot of type O people in my blood drive. And that is this new binomial model, which helps us with kind of difficult probability problems. Now there are a few caveats to it. There's a few things that we need to know about the binomial model. One, these are kind of like our conditions. There's 2 parts to our conditions. One is that we needed a success-fail model. So there could only be 2 outcomes. It's not like I could have been like, what's the probability that out of 8 donors, 3 are type A and 2 are type O? That would be introducing more successes. I needed to have only one type of success, only one success here. Okay, so we needed this success-fail model where there's a success, there's a P, and there's a Q. Okay, and we need to make sure that our probability stays the same every time, meaning that it's independent. We were talking about blood type in the US. There are 327 or something million people in the United States, like a crap ton of people. As I start to take people out, there's so many people in the US that it doesn't really matter. But if I had a smaller population and I started taking out and I was using those fractions, that probability would change every time. So we need to make sure we had a large enough population that the P stays the same every time. Okay, so those are our conditions on using this binomial model. All right, I'm going to give you a couple for you to try, and then I'll show you the answers. You can pause the video, and then we'll look at the answers. So I'll put our chart back here. You have it in your notes, but you know. Okay. Let's say you are desperate to have AB blood type because you have this patient and they're like, oh, they have AB blood type, it's really rare. So you're like, I want the probability that out of 10 people who come into your blood drive, at least 1 is type AB. Okay, let's say you have 2 patients who are type A. What about the probability that out of 10, exactly 2 are type A? And let's say you have 4 patients that are type B and you want type B blood. Let's see what's the probability of not having enough for them. So the probability that out of, I don't know, we'll keep it at 10. Less than 4 are type B. So pause the video now and try these 3 probabilities, and then I'll go through them right now. Okay, so out of 10, at least 1 is type AB. So I'm looking at these 10 people. I want at least 1 to be type AB. So I want 1 or more. Now it's the right-hand side, and the calculator can only give me the left-hand side. It said at least. So I need to be thinking everything except this 1. I want to take away 0. So everything except 0. And this is type AB. So my success is type AB. And I'm taking away the 0. So we've done this before, at least one, where we did everything except what we don't want, which is none that are type AB. None that are type AB. So we could do that. Oops. 0.335. So there is a 34% chance or so that out of 10 people you'll find one that's type AB for your patient. So there is a chance. Not greater than 50%, you might want to get more people in there, but okay, so out of 10, exactly 2 are type A. So it's not like we're trying to find more than or less than. We want exactly 2, so we want just this one, which means that we can be like, okay, type A. I want exactly 2 type A's out of 10. So out of 10, I want 2 that are type A, which means the rest I want to be, so the 8 other ones are not type A. But then how many different ways can I make that happen? So out of 10, how many ways can I make 2 successes? And so I've typed that in my calculator. So 10, math, PRB. If you have like a basic calculator, you'll see this on the basic calculator. I wanted exactly 2. So 45 times 0.42 squared times 0.58 to the 8th. 0.1017. Okay, and the last one, out of 10, less than 4 are type B. So I don't want exactly, I want less than 4. So not 4, less than 4. So I want 0, 1, 2, and 3. So this is me not being successful in getting less than 4 that are type B. So that's 1, oh no, not 1 minus, because I do want the left side. So this is just binomial CDF. I want it to add up the probability of getting 0, 1, 2, or 3, anything less than 4. So 10. Type B is 0.10. And up to 3. And so I type that in. Second vars. Binomial CDF. Out of 10, the probability of B is 0.10 up to 3. 0.987. So there is a very strong chance that I won't have enough type B if I had 4 type B patients. Okay, this is the binomial model. If you have a large enough sample, let's say you had out of, I don't know, 100, you could approximate normally, right? Because we know that, this is just a side note. Just a little side note. If your sample is large enough, you can do a normal approximation. So let's say we had out of 100, what is the probability less than, I don't know, 20 are type B? Oops. Now we are satisfying our conditions for normality. Barely, but we are, because now it's big enough. Remember, this is our P, and so we're really doing like that PQ over N, where we're like, okay, our P is 0.10, but there could be some variation, and we have out of 100, so that's our n. Okay, and this is something that we did back in the day where we could use a normal approximation. We don't have to now that we know binomial. We can do binomial, but we also can do a normal approximation where we're like, okay, the standard deviation is a square root of p q over n, just to give you a little throwback. .03. Okay, but this normal approximation is just that, an approximation. So actually the binomial model is probably a little bit better than the approximation, but we use our approximation so that we can make confidence intervals and stuff like that. But we can do this where it's like, what is the probability then less than 20 out of 100? 20 out of 100 is 0.2. So we want less than 0.2. Ooh. It's going to be a very high percent. Less than 20 are type B. So there's a very strong probability that less than 20 are type B. Okay, or we can do the binomial CDF where we're saying out of 100, so out of 100, less than 20 are type B. So out of 100, type B is 0.10, less than 20. So add up to 19 for me. And we should be able to find that probability using binomial CDF or by finding a z-score and using normal CDF. They'll be a little bit different, but you'll still get about a similar probability. They might be off by like 5%, but you'll get a similar probability. Shall we just find it? Binomial CDF 100.10 19 99.998 is what we get with binomial CDF. And if we do it with the normal approximation, we need to find a z-score. That's what it means when we draw a line on our curve like this. So 4.20, our z-score is 0.20 minus the center divided by the standard deviation. So 3.3 repeating. And so we want to find from 3.3 all the way down to negative 999. If we remember doing this stuff. So let's see if we get something similar. Normal CDF, negative 999, 3.33, enter, enter. 0.999. So basically the same thing. Okay, very similar probabilities. They're not exactly the same because this is an approximation and this is a theoretical probability, but you'll get similar things. So if you have a big enough sample, you can use a normal approximation, but if it can't be approximated normally, now we know that we can use this binomial model. And that is everything. Please do the Khan Academy associated with the binomial model, and then we will have a worksheet where I combine all the probabilities for us to work on, and then we're almost done with probability. Okay, good luck.